Alright, so today we're going to talk about balancing chemical equations. Now, there was a video about this last week on an Edpuzzle that introduced some of these concepts that I'm going to be going over again today. But really, I just wanted to go over how I would recommend you do it, which may or may not align with what the video said. And if there's something in the video that made more sense to you than what I'm about to share with you, that's fine by me. Whatever works. But I'm going to first explain the sort of concepts involved, a lot of which we talked about last week in the review and are based on things that we have already done. And then I'm going to go through the process, the steps that I recommend you take in order to balance an equation. And you may find a way that works a little bit differently, or see something you can look up online, obviously, a process that works a little differently. That's fine. Whatever works, whatever makes the most sense to you. So, first of all, if you didn't watch, first of all, the video on counting atoms, or the exercise on counting atoms, which I believe was the first assignment from last week, review assignment from last week, or if you did not see the Edpuzzle on balancing equations, you might want to revisit those. You might want to just finish this video and see how it works, and then maybe go back and watch those. Because again, all of that, for the most part, was review of stuff we've already covered. So maybe you remember how to count atoms in a formula and that sort of thing. But we're going to talk about the parts of a chemical equation, how to read a chemical equation. We'll revisit something called the law of conservation of mass, and go through the process of balancing chemical equations. And then the rest of the week, we're going to look at more chemical equations, but instead of just looking at the count of atoms on both sides and getting the equation balanced, we're going to look at the features of different types of reactions, and how do you identify something as being combustion, or replacement, or combination, or decomposition. There are different classes of reactions, and we'll go over how you can tell by looking at an equation what each type of reaction is. So quickly, just to start with, a relatively simple reaction. H2 plus O2 produces H2O. Write that a little bit. Didn't give myself enough room. H2O. Okay, so there's a few things to look at in this equation. They're true of all equations. All right, there's the arrow here in the middle, which you can think of as being like the equal sign in a math equation. Okay, it separates one side of the equation from the other. And when we're talking about balancing, we need to take into account the left and the right hand side of the arrow, what are called the reactants, which are the starting material, or sort of the ingredients, on the left, and the products. In some cases there might be one product or products that are on the right. Okay, so we're looking at the left and the right, the reactants and the products. The formulas and subscripts, again, we talked about and reviewed last week, so if you need to look at that again, you can go back and watch any of the videos about that from last week. The last little piece that I want to highlight here is the plus sign. Okay, the plus sign separates one substance from another. So this is H2 plus O2. Those are two separate things in the equation. Over here, where there's no plus sign, that means that everything on this side of the equation is one compound, one substance. So that's important in terms of when we start putting in what are called the coefficients. The plus sign sort of defines where the effect of the coefficient starts and stops. And also later on, when we're looking at types of reactions, the plus sign, the presence or absence of a plus sign on one side or the other will be one thing we can look at to identify the different types of reactions. So the first thing to look at is counting up the atoms on each side of the arrow. How many atoms are on the reactant side? How many atoms are on the product side? So let's take a look. So we've got H2. So that means that there are 2 hydrogen atoms. And then we have O2, so that means there are 2 oxygen atoms. Okay, on the left-hand side, the reactant side of the equation. On the right, products, we have H2, so 2 hydrogen, O with no subscript. So that means on the right-hand side, there's 1 oxygen. Okay, that looks like 10, but that's a 1O. So the problem with this is that we have 2 hydrogens on both sides, which is good. But on the left we have 2 oxygen, on the right we have 1 oxygen. According to the law of conservation of mass, atoms don't just disappear or appear out of nowhere during a chemical reaction. You can't create or destroy an atom during a chemical reaction. So that means that the equation has to be balanced. We have to have the same number of each element on both sides. So right now this equation is not balanced, which is something we would call a skeleton equation. It has all the right stuff in it, but not necessarily in the right quantities. But it's our starting point. So we can't change the formula, right? Because H2O, if I say, well, I need 2 oxygen, so let's make that H2O2. Well, H2O2 is hydrogen peroxide, it's not water. So I can't just change the formula. That violates another couple of laws we have called definite proportions and constant composition, which says H2O is water, and water is always H2O. If you change any of the numbers in here, well, that changes it into something else. And H2 is always H2 when it's an elemental molecule. It's never just H and it's never just O. So we can't ever mess around with the little numbers called subscripts. But we can use something that I touched on last week called a coefficient. Okay? A coefficient is a number that we put in front of a substance that multiplies the number of units of that substance. Okay, so I'm gonna I don't have the colors to match up quite here, but I'm gonna bring back the Legos from last week. So this is 2 hydrogen, and then we have 2 oxygen. Okay, that's what's on this side. On this side we have the 2 hydrogen, and we have the 1 oxygen. Now, here's the trick. These 2 hydrogens are stuck together. These 2 oxygens are stuck together, and the 2 hydrogens are stuck to the 1 oxygen. Okay, so again, just looking at it in terms of the molecules, I can't alter these bricks the way they're connected. But I can have multiple units of each substance, and that's what the coefficients allow us to do. So if we took, for example, the water molecule, and you said, well, what if I had 2 water molecules? This number here is called a coefficient. Okay, coefficient. Okay, it's a number that we put in front of a substance in an equation, and it means that there are 2 water molecules. So if I now look at that, make another water molecule, another H2O. Okay, well, now let's count it up. It's 2 times H2, which we can see, H2, H2, so H2 twice. Now that means instead of 2 hydrogen, I actually have 4 hydrogen. Right, so we can update that. And instead of the 1 oxygen I had in my first water molecule, now with 2 water molecules, I have 2 oxygen. Okay, so the 2 water molecules give me 4 hydrogen and 2 oxygen. Now if we go back to the left hand side, you can see that, well, now we have 2 oxygen, which is great, but now we only have 2 hydrogen here and we have 4 hydrogen over here. So we kind of fixed one problem and made another. That's okay, because what we can do now, right, is if I need 4 hydrogen and I've got 2, well, I can put a 2 in front of that hydrogen, which means now I have 2 hydrogen molecules. Each hydrogen molecule has 2 hydrogens. Okay, so now instead of 2 hydrogen, I have 4 hydrogen. Okay, so by using these coefficients, 2H2 plus, there's an imaginary 1 there, 2H2 plus O2 produces 2H2O. So 4 hydrogens plus 2 oxygens produce 2H2O, which is 4 hydrogen and 2 oxygen. So the numbers are now balanced. All right, now let's take a look at each another equation, and I'm going to go through a little bit more in detail sort of how I recommend attacking this type of problem. There's a few things that you can look for, a few sort of tips and tricks that you can try that might make it easier, because there's lots of different ways to do it, but I'm going to give you the way that I find works best. Okay, so let's take a look at another equation. Okay, so we have aluminum and bromine produces aluminum bromide. Okay, so that's a different equation. Again, not a lot of different elements, not a lot of subscripts and compounds, but the first thing you want to do, okay, is tally up the atoms on both sides. I like to draw a line down the middle below the arrow that kind of really distinguishes the left and the right, the reactants and the products. Helps me keep track of stuff. So let's count up. Again, we have two elements. I'll use two different colors. So we have one aluminum on this side, and we have one aluminum on this side. On the left, we have Br2, so that's 2 bromines. And on the right, we have 3 bromines, Br3. Okay, so the aluminum, it's all set. But the bromine is 2 on the left and 3 on the right, which again breaks the first rule. So the first thing that I always say is, if it's not broke, don't fix it, right? That's a classic rule. In other words, I'm not going to mess with the aluminum on purpose, at least not right away, because it's already balanced. So if I don't have to touch it, I won't. Doesn't mean I'm not going to, but I don't start there. Obviously, I'm going to start here where there's a difference. And I have to look at the fact that this is a Br2, and I can't do anything about that little number. And this is a Br3, and I can't do anything about that little number. So I can't change the 2 or the 3, which means I have to start thinking about how am I going to multiply these two numbers so that I end up with something that's balanced. Well, there's something called the least common multiple, right? What's the smallest number that they both go into? It's 6. So how do I get a 2 to be a 6? I multiply by 3. Remember, the coefficient is multiplying, not adding. That's something that confuses some people. And over here I've got a 3, so if I put a 2 here, it's 2 times 3, which is 6. So now this becomes a 6, because it's 3 times 2, and this becomes a 6. So once you start putting in coefficients, the absolutely positively most important thing is to carefully keep track of every change you make. Because if you change something and don't sort of update your numbers, and then you go and change something else, the numbers are going to stop making sense. They're going to stop working out because you've made a change that you didn't account for. So I fixed the bromine. Now the problem here is that by putting this coefficient in front of the aluminum bromide, that's one substance, right? There's no plus sign in there. So this number 2 affects the aluminum and the bromine. The bromine I needed. The aluminum, I didn't need to change it, but I didn't have a choice because the bromine's attached to it. So I have changed the aluminum from a 1 to a 2 because it's 2 times aluminum. All right, now I've broken the balance of the aluminum, but over here I've got aluminum all by itself with no subscript and a plus sign next to it, which means if I change this aluminum over here, it doesn't affect anything else on that side of the equation. So I can put a 2 here, which will then make this 2 aluminum. Now again, just to, if you want to look at the way this works with the Legos, right? I started with 1 aluminum, which is just an atom of aluminum by itself. Now I have 2 aluminums. 2 aluminums. Okay, 3 Br2 means, well, I started with just Br2, just one of them. That's a unit that I can't break. But by putting a 3 in front of it, it means now that I have 3 Br2s. So 6 altogether. On this side, I started with 1 unit of Br3. Oh, sorry, AlBr3 that I cannot break. Okay, 1 aluminum, 3 bromines. What I did then was I put a 2 in front of it, which means 2 units of AlBr3. So there's a second unit of AlBr3. Now I have 2 aluminums and 1, 2, 3, 4, 5, 6 bromines. So the same number of bricks of each color on both sides, and but they've just been rearranged, and that's all chemical reactions are. They're just moving atoms around. So if I wanted to, right, and this is kind of might be helpful to see, right? So let's just say, because remember what we're doing in this reaction is we're starting with 2 aluminum atoms and 3 bromine molecules with 2 bromines each, and we're having a reaction that creates 2 units of aluminum bromide. Well, if I take these apart and rearrange them, I have taken only the bricks that were over here and I've made them into the compound that's over here. I've used up all the bricks I started with, I don't have any left over, and I didn't lose any along the way. So it's the same bricks on both sides. Okay, same bricks, you know, there's no camera magic here. That's all it is. And that's what balancing a chemical reaction is for. Because the bricks I have over here, that's all I have. Okay, I can't, you know, in the middle of the reaction say, oops, I need to change this around and I'm just going to get rid of, you know, one of these blue bricks because it doesn't work out that way. No, you can't do that. You can add more units of aluminum, you can add more units of bromine, and you'll get more units of aluminum bromide, which is another thing that we'll talk about next week called stoichiometry. But I can't change the ratio, right? This is a recipe. I can't change the recipe. So that's that. Okay, so let's take a look at a reaction that has 3 elements. So propane, which is C3H8, reacts with oxygen to form, I'll move this down a little bit, propane plus oxygen produces CO2 and water. Okay, this is what's called a combustion reaction. It's what happens when you have a propane grill or a propane stove. You take the propane gas, that's what that molecule is. You react it with the oxygen in the air, and that releases the fire, the heat. It releases the heat and the light that you see, that's the fire. And the products are carbon dioxide and water. Now that's in a perfect world. There are actually other products that typically get produced, but this is the base reaction that we're talking about. Okay, so let's balance this equation. Okay, first tally up the elements. Now we've got 3 different elements. Start with C. Okay, there's 3 carbon. There's 8 hydrogen. And there's 2 oxygen. Okay, on the other side, I have a carbon, 1 carbon. I have 2 hydrogen in the H2O. Now here's one thing that you'll come across, and how you handle this depends. I like to look at all of the oxygens together. You could say, all right, this is O2 and then this is another O. That's possible, and you can make it work. I like to just say, all right, there's 2 here and 1 here, so that's 3 oxygen altogether. Okay, again, I could look at that as 2 oxygen and 1 oxygen separately and then make it work out. Okay, so none of the elements in this starting equation are balanced. So let's see if I can do this with the bricks that I have here. Okay, and again, these when I put these bricks together, these are not by any means what the molecules actually look like. C3H8 doesn't look anything like that. And then O2 will be these blue ones. On the other side, I have CO2 and no, that's right, CO2 and then H2O. Okay, so there's the numbers. None of it's balanced. I can't change any of the formulas at all. So now I have to look at, okay, where do I want to start? Here's a couple of things that I will suggest. First of all, when you have an element like oxygen that's alone by it, even though there's O2, there's just oxygen here, there's no other element connected to it, don't start there. As a rule, don't start with water. From there, it's kind of dealer's choice, right? I'm going to start with the carbon because there's a 3 and a 1, and I can see a pretty easy way to fix that, because if I put a 3 in front of the CO2, it makes this 3 carbon, right? Because I have now 3 CO2, 3 CO2, 1, 2, 3 carbons. I did also just change the number of oxygens. Okay, by multiplying the 3 times the CO2, now I have 6 oxygens here, and don't forget about this one over here. Okay, so the total is 1, 2, 3, 4, 5, 6, 7 oxygen. Okay, so I kind of fixed one thing again and made this difference even bigger, but we'll come back to that. All right, now I've got hydrogen, where I've got 8 on one side and 2 on the other. Well, if I put a 4 in front of the H2O, now I've got, I may have messed this up a little bit too. Here's another water. Here's another water, and here's another water. Okay, those are 2 hydrogen, so 4 H2O. Okay, we'll make these look the same. Okay, there's your water molecules. So now I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. I have also again changed the number of oxygens because 4 affects the whole H2O. So 1, 2, 3, 4, and then I had 6 over here. So now I have 10 oxygen, 8 hydrogen, 3 carbon. So the carbon, the hydrogen are matched, the oxygen is not. But because I left this oxygen alone, and because it's by itself, I can add a coefficient to it of 5, because I want to get from 2 to 10, and I have to multiply, not add. Well, if I have 5 oxygen molecules, One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 5 O2s. 5 times 2 is 10. Now I've balanced the equation. Okay, so that's how you balance the equations. There's been a couple different examples. In general, okay, and actually some of these combustion reactions will be the exceptions. In general, your coefficients are going to be in the single digits, typically, between 2 and 5. Doesn't mean they can't be bigger, and sometimes they will be bigger. But if you start getting into double-digit coefficients, like you go around and say, oh, now I got to multiply this by, you get a 10 here instead of a 5, just slow down. It's not impossible, and you might not be wrong, but once you get to 10 and you start getting into these bigger and bigger numbers, it may mean that what you did is you did something double, right? Maybe this only needed to be times 2 instead of 4. That wasn't the case here, but you have these things where if you look at something, you might think the smallest common multiple is twice as big as it really is, and then you can get into these bigger numbers. So the last thing to check, because this would be, if you did this out, you could end up with this, and you would actually have a balanced equation. This is the last thing. Okay. And the bricks don't matter here because I don't have enough. But if I did 2 times C3, that'd be C6. 2 times H8 is 16. And 10 times O2 would be 20 oxygen. And on this side, I have 6 carbons. I have 8 times H2, which is 16 hydrogens. And I have 6 times O2, which is 12, and then 8 times O, which is 8. So 12 plus 8 is 20. Oop, didn't match the color, but that's okay. So you can see that this is actually balanced, but a chemical reaction should always have the smallest coefficients possible. So since all of these can be divided by 2, and if I divide them all by 2 and I count them up again, they're still balanced, you need to simplify, reduce those numbers. Okay, so that's it for balancing equations. There's going to be a Google form worksheet for you to practice some of these on your own. Do that worksheet online. It's just a Google form online, and then we'll be talking about different types of reactions starting in the next lesson.